Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Traditional people ask questions online, or they wait until mentioned?
Some people get kind of slowly.
I think it's better because on the subject is fresh and physical.
Questions. Okay, good morning. I'm pleased to introduce Petr Kuznetsov, who's here for interview today and tomorrow. He's from EPFL and will be talking about his thesis work, which has been on using failure detection in synchronization problems.
Okay. Thank you very much. Well, since it's an interview talk, I would like to start from saying a few words about myself. And I was born in St. Petersburg, Russia, Leningrad, USSR back then. I did my undergraduate studies in the St. Petersburg Institute of Fine Mechanics and Optics Technical University. And in parallel, I've been collaborating with Delft University of Technology. And the result of this collaboration constituted my master thesis in mathematics in 1997. And before that, concurrently, and after that, I've been working as a systems engineer in the area of computer networking for the Business Computer Center in St. Petersburg, which is one of the most successful systems integrator companies in Russia. And in 1999, I got a fellowship for graduate studies from the EPFL, Swiss Institute of Technology in Lausanne. And in 2000, I joined the Distributed Programming Lab as a research assistant, and in 2001 as a PhD student. Today I'm going to talk about my PhD studies, and in fact, I've been involved in a number of projects during this PhD term, and this included design and analysis of epidemic algorithms for overlay networks, which resulted in a lightweight probabilistic broadcast algorithm, a novel gossip-based multicast algorithm, and the delta reliability, a novel measure for broadcast reliability. I also did some work on exploring the intersection between the algebraic topology theory and distributed computing theory. Also, I concentrated on using failure detectors and solving synchronization problems in distributed computing. And recently I drifted towards abstraction-free algorithms and solo-fast algorithms. Those algorithms are using the absence of contention in distributed environments. And since my thesis is on failure detectors, I focus on the third point today. And in my thesis, I've determined a number of weakest failure detectors for various problems in distributed computing. And in particular, for non-blocking atomic commit, this problem arises in distributed transaction processing. And fault-tolerant mutual exclusion, this problem is inspired by implementing indivisible resources in a distributed environment in a fault-tolerant manner, and boosting synchronization power of atomic objects. And the last result is the most recent one, so I concentrate mostly on this in this talk. So I will start from giving a motivation. So why this problem is interesting, why the results we are obtaining are important. And then I will try to be a bit more formal and introduce the model of computation we are considering. And then I try to give the intuition of how the result is actually obtained and conclude with some side remarks. So why actually this is an interesting question? The main motivation is the following. So assume we are given a shared memory system and we have a number of base objects and a number of concurrent threads, which we call processes, want to implement another abstraction, another object. Which objects can be implemented in a fault-tolerant manner? And fault-tolerant here means that every process makes progress on the implemented object, regardless of the failures of other processes. So this question actually is inspired by the state machine replication problem introduced by Lamport in late 70s. In this problem, we have a state machine, and we want to make it highly available by putting it in a number of redundant components, so that the failures of particular components do not block the whole service. So it turns out that the components should be synchronized in some manner to make sure that the overall implementation is consistent. And in this sense, the most interesting object to implement is consensus. In consensus can be seen as a task. So it's a task where processes start with some values, which say they propose values, and they eventually must agree on the common decision value. So, for instance, they start with values 0, 1, and 2, and after some computation, they should agree on the common value 1, which is one of the proposed values. Why consensus is important? Because consensus is universal. Using a supply of consensus objects and some simple, reliable communications like read and write operations, we can implement any object with sequential specification. We can implement any state machine. And a natural question is whether consensus itself can be implemented from reads and writes in a fault-tolerant manner. Or more precisely, let's assume that processes communicate through reading and writing in the shared memory, and the processes can fail. And fail here means that they can stop prematurely taking steps of their computation. We say that they fail by crashing. And we assume that processing is asynchronous, meaning that there are no bounds on relative processor speeds. So there are no bound phi such that in any execution, whenever a process takes phi steps, every correct, meaning not yet crashed process, will take at least one step during this interval. So we cannot build our algorithms based on such bounds. And designing a consensus algorithm in this system would be very appealing, because that would mean that we can actually implement any state machine in a fault-tolerant manner for free, given just simple communication. That would mean that there's no difference between distributed computing and centralized computing. And unfortunately, or maybe fortunately for us, is that it's impossible. So it's known that consensus is impossible if at least one process might crash. So no matter how many processes try to synchronize, if at least one of them might crash, and the system is asynchronous and communication is read-write, then consensus is impossible. So there is a number of researchers which obtained this result, and all of these impossibility proofs are in a sense inspired by the fundamental proof of Fisher, Lynch, and Patterson for message passing systems. So if you have, let's say, 3 processes, there is an execution in which one of them might crash or might not crash, but processes cannot decide on a value without violating safety properties of consensus. So let's try to ask a question, why it's impossible. One of the possible explanations is that we lack synchrony. So the system is asynchronous. So we don't have any means of reasoning about who's there by taking locally some computational steps. So that brought us to the definition of failure detectors. Failure detector is an abstraction which gives some kind of synchrony to the processes. It turns out that this is useful for achieving consensus. The other perspective is that the communication is too weak. So this read and write is just too weak to achieve synchronization. And modern computing systems sometimes have more powerful communication primitives like compare and swap. And those primitives sometimes let us implement consensus. And this is another perspective on the impossibility. So let's start from the first one. So in a synchronous system, there's no way to ever distinguish a crashed process from a very slow one, sleeping one, no matter how many steps you locally take. So if you consider this scenario, we have process Q which crashed from the very beginning. And process P takes a number of steps, reading and writing. And after some time, it wants to decide whether Q is up or down. But it cannot do so because this situation is indistinguishable from this one, where Q just takes a right step and then sleeps for a while. So we might think of adding some more synchrony to the system. So let's assume that there is an unknown a priori bound phi, such that whenever a process takes phi plus 1 steps, every correct process or every not yet crashed process takes at least one step during this interval. So in this example, this phi is 1. So process P1 and P2 both takes 2 steps. And during this interval, process P3 makes a right operation. So there is an information flow from P3 to P1 and P2. And P1 and P2, they see the presence of P3. So in a sense, P3 is kind of a leader in this computation. So we can try to abstract this information out in a form of a distributed oracle. So yeah.
Some correct process takes a step.
Yeah.
But in your words, you said every correct process takes a step.
No, that was okay. I did mistake. Yes, some correct process, not necessarily every, but some correct process takes a step during this interval. We don't know which one, but
then, whenever a process takes 5 plus 1 steps, at least that process has taken 1 step. So isn't this condition vacuously satisfied?
yeah, the condition is the following: that whenever, if we consider the whole execution, and we take the execution in which interval in which every process takes 5 plus 1 steps.
Oh, every process.
Yeah, and during this interval there is one process. Okay, let's put it this way. So there is an interval during which some process takes 5 plus 1 steps, right? And there is some process which takes at least 1 step during this interval. Okay, well it could be this process which took, but let's take another execution with the other process takes 5 plus 1 steps. And we require then during this interval the very same process which was participating in the first interval also seen in the second one. So there must be one process which is seen by all processes which take 5 plus 1 steps. You see the point? So there is kind of a process which can be used as a coordinator. So like here, this is P3. So whenever P1 takes 2 steps, or P2 takes 2 steps, during both intervals, there is P3 which is there. Okay, so it somehow gives the intuition why we can use it for achieving coordination between the processes. Yeah?
So perhaps this statement...
Yeah, the statement is yeah.
There is a process P, such that whenever another process
Exactly.
takes 5 plus 1 steps, it takes 1.
Right. I tried to make it shorter, but I wasn't very successful. So let's as you say, there is a coordinator. So we can try to abstract this out in the form of an oracle. So assume that every process has some information from some oracle, which gives a process ID at any moment of time. And this oracle guarantees that eventually the very same correct process is output at all processes. Okay? So coming back to this example, we have 4 processes. P4 is crashed from the very beginning, and up to some moment of time, some various process IDs are output. But there is a moment of time after which exactly one process is output for correct processes, and this is P3. So assume we have this information. So we are provided by the system, we are provided this oracle. Yeah.
Would that mean that P3 then could not crash?
No. Correct means, yeah.
The elected leader.
Correct means that it never crashes. Okay, so if P3 crashes, then omega should provide some other process which is not crashed from this time on.
What happens if omega is already provided?
Okay, yeah.
Then P3 dies.
Of course, in this sense, correct means we can say that the process is correct or not, only considering the infinite execution, right? So that's assume we have an infinite execution. I cannot draw the infinite execution here. I have to put a fragment. So that's the. But later on, we will model failures in terms of events in the computation. This is more somehow suitable for failure detection. And it turns out that if we are given this oracle, then we can solve consensus tolerating any number of failures using read-write memory. And even more interesting is that omega is exactly what we need. So Chandra Hatzilakos and more precisely Lloyd Hatzilakos for shared memory, they've shown that the information about synchrony provided by omega is sufficient and necessary for solving consensus in a fault-tolerant manner. Let's come back to the question why consensus is impossible in asynchronous systems. And the other perspective is that we lack powerful communication. So let's assume that we have more powerful communication primitives like component swap or test and sets or queues or whatever. We have some other objects. And it turns out that in some cases it helps us to achieve agreement. So we can assume that processes communicate using invoking operations and receiving responses from atomic objects. An atomic object is an instance of an object type which specifies the interface of the object, which is the set of states which the object can take, the set of operations which can accept from the clients, and the set of possible state transition sequences, which is the sequential specification of the object. For example, you can consider a register type, which provides the usual read-write semantics, which has 2 operations, write and read, and write stores the value in the register, and read returns the last written value. And the FIFO queue provides NQ and DQ. NQ put the value to the end of the queue, and the queue returns the first item in the queue. And in some cases, these atomic objects, they help us to achieve consensus. But sometimes the power of these objects is limited. And we can define the power of the consensus power of a type as the maximum number of processes among which consensus can be solved using registers and atomic objects of this type. As we've shown, consensus power of register is 1. We cannot achieve consensus in a fault-tolerant manner among 2 or more processes using registers. Consensus power of Q is 2. We can actually solve consensus using 1 queue and 2 registers among 2 processes. But it's not possible among 3. And consensus power of a component swap object is infinity, so it's sufficient. We just can have 1 powerful component swap operations to achieve consensus among any number of processes. So we are coming to a more general impossibility. So assume we are given a type T with consensus power n. And by definition, this type cannot be used for achieving consensus among n plus 1 processes or more. Again, we might ask, what's the problem? Can we add some more synchrony? Because remember that the system is still asynchronous. So can we assume more synchrony in the system to be able to solve consensus using this type. And the other question is how much exactly synchrony we need. Okay, so we are approaching now the main question of the talk. And before that, I will present in a slightly more formal manner the model of computation. Assume we have a set pi of k processes, p1 to pk, which communicate using a collection of registers and some objects of type t. So the only thing which we know about this type is that it has consensus power n. And since, to make things interesting, we should consider probably that k is strictly more than n, because otherwise we cannot solve consensus already. So since the consensus is impossible if k is strictly more than n, then we add some information about failures. And this information is encapsulated in the failure detector abstraction. And every process can query its failure detector module. And this module produces some maybe incomplete and inaccurate information about failures. What's important here is that the information which is provided by failure detector is based only on failures. So it cannot reveal some information about the local state of variables in the processes. So this failure detector abstraction is added to the system in a modular way. So it doesn't depend on the concrete steps of the processes. So here we assume that there is some event which is a crash event, which can be used by a failure detector to transmit some information about failures to processes. And to be able to compare failure detectors, we introduce some kind of a partial order. We say that a failure detector G is weaker than failure detector G prime if the output of G can be extracted from the output of G prime in the following sense. So there is a distributed algorithm that uses the output of G prime to simulate the output of G. So it gets the information of failures provided by G prime, communicates among processes, and at every process we simulate the failure detector module of G. Okay? Yeah.
Is this failure detecting attached to Q? Is it answering the question? Has P failed? Or does it answer questions about which other processes have failed?
It can produce any information. I don't restrict it to this set of processes which are suspected to fail, or to be. It can be a binary function on the failures happened so far. It can be a process ID like this omega. It can be a set of suspected processes. Anything. So the only thing is that this information encodes the failure pattern. It's not based on the states of the process. Okay. So respectively, we define this partial order. So we want to define the weakest failure detector to solve a given problem. In our case, it's consensus, using some communication primitives. In our case, using registers and objects of type T. And we say that D is the weakest failure detector to solve consensus in our system if D is sufficient to solve consensus, which means that there is an algorithm that solves consensus using D. And D is also necessary in the sense that any failure detector G prime which is sufficient can be transformed into D. So D is weaker than any failure detector G prime which is sufficient to solve consensus. So now we are coming to the technical part of the talk, which is the, I will try to convey the intuition how we actually obtain this weakest failure detector. So the main question is, what is the weakest failure detector to solve consensus using registers and objects of type T, such that consensus power of T is n. And the reasonable candidate to answer this question was introduced by Gil Niger in 1995. And he specifies the failure detector omega n, which outputs at all times and at every process a set of at most n processes. Yeah.
Is it clear why there should be such a
actually not. It's not necessarily there. So you might think that, okay, maybe there is no weakest failure detector. But for some problems, we can identify it. So, and of course, this maybe coming back, I just this definition, it doesn't show that there is a unique failure detector which satisfies this property. So in a sense, maybe technically correct would be say that there is a weakest failure detector, because there are maybe a number of, but in some sense they are all equivalent. They can be transformed in each other. So here we propose a candidate for the weakest failure detector to solve consensus on our system. Okay, this failure, well, in this scenario we assume that n is equal to 2. So at every process and at all times it outputs a set of 2 processes. Up to some time it can be any sets. But there is a moment of time after which it outputs the same set of 2 processes at all processes. And this set includes at least one correct process. And in this case it's P1 because P4 is already crashed. Okay? So it's in a sense it's a generalization of this omega oracle. Niger has shown that omega n is sufficient to solve consensus using, well, among k processes using objects of type T and registers. But the question whether omega n is indeed necessary remained open. Our contribution is that we show that indeed, yes, omega n is necessary if the type T is deterministic, meaning that every operation on the object of this type triggers at most one state transition. And it's also one-shot, meaning that in any execution, a process is allowed to take at most one operation on an instant of this type. Yeah.
That's quite drastic.
Drastic.
Only one operation on each.
By one process, yeah.
By one process.
Yeah. So you have every process can access the object, but at most once in the computation. So it looks like, in a sense, it looks like, for instance, a consensus object is a one-shot object. Because you can access it twice, but you get the same information from it. Because it has this greening property. So there is some amount of research on the one-shot types, and it turns out that they expose quite interesting behavior in different scenarios. So it's not too limiting, I would say. So our aim is to present a reduction algorithm. So we assume that there is an algorithm A that solves consensus using some failure detector G, registers and objects of type T, and we use this output of this failure detector G and this algorithm A to simulate the output of omega. So how we do it? So we proceed in 3 steps. First, we we generalize the technique of Chandra, Hatzilakos, and Toik, which is probably one of the most fundamental results in this research domain, where they define the weakest failure detector for solving consensus using message passing. So we use this technique of failure detector sampling and local simulation at the processes, and we generalize it in a suitable manner. And we introduce a new construct in the proof, which we call a rake, and then we use this construct to simulate omega n. So we'll start from the first point. In the reduction algorithm, every process runs in parallel 2 components. One is called communication component, and the other one is called computation component. The communication component is responsible for acquiring the failure detector module G and transmit this information to all other processes. So they exchange all this information, they build some kind of a structure, and then the computation component uses this structure to simulate the output of omega n. So more precisely, the communication component constructs an ever-growing failure detector sample DAG, directed acyclic graph, which encapsulates a sample of failure detector output at different processes, and also some kind of temporal relations between the values which are seen by different processes at different times. And the computation component uses this DAG to locally simulate the overall system in which processes run the given algorithm A. So what is this DAG? It's directed acyclic graph. A vertex is a tuple PDK, where P is the process ID, D is a value which is seen by process P at its failure detector module, and K is the time, how how many times the process queried its failure detector so far. And an edge in the DAG from PGK to P prime G prime K prime means that P saw G at its failure detector module after it kth query before P prime saw G prime. For example, it might mean that P queried its failure detector module, got the value G, then it's written the value in the shared memory, then process P prime has read the value here, and then queried its failure detector module and got the value G prime. There is a causal relation between these two events. So that's what the edge at the graph mean. In the computation component, every process periodically uses these DAGs to simulate executions of A. In the simulated environment, we assume that processes propose values in 0 and 1, so they propose binary values. So and for any initial state, we start, and for every path in this DAG, so we have a number of failure detector values according to the order they were seen, and the initial state and the path induce an execution of A. A is an algorithm, so we know it. So an algorithm can be seen as a state machine. So we know at every moment of time, given the state of a process and the value it sees in the failure detector module, or the result of last operation on a shared object, we can compute the next state of the process. And the algorithms are deterministic. I didn't say it before, but we assume that the algorithms are deterministic. And all these possible simulations give us a simulation forest. A forest is a collection of trees, one for each initial state. Okay? And since A is a consensus algorithm, and in simulation forest, it's ever growing, so it encapsulates more and more simulations, and the simulation gets longer and longer. So there are some simulations in which some process takes enough steps to decide. So in this consensus algorithm. And we tag the vertices of the tree according to the values which are decided in the descendants of these vertices. So let's consider this situation where you have some fragment of the tree. So let's say some vertex is extended with a step of P where value G is seen. Then it's extended by a step of P of Q where G prime is seen. Or alternatives can be extended by a step of R, which is an access to some shared objects instead of querying failure detector. And assume Q, after taking this step, decides 0, R decides 1, and assume R applied to the root of this tree decide 1. Okay? So then we can put the tags on the vertices. So the root of this subtree has both vertices, both tags, because there is a descendant in which 0 is decided, and there is a descendant in which 1 is decided. So that means that we have both tags on the vertex. This vertex also has both tags. And the vertex in which some process decides can have exactly one tag. Why is it? Because since the process decides, there's no extension of the state in which some other process decides differently. So this is not allowable by consensus. Okay? And we call the vertices in which have both tags, we call them bivalent. And the vertices which have just one step, we call univalent, which are 0 valent or 1 valent. Okay? And so yeah.
I'm getting a bit lost about this, how you built this DAG in the first place. So in the diagram you said, oh, well, so my reader triple, you have these triples, right? And then there's this right and read. And you're saying this DAG is constructed as the algorithm runs by the failure detector, is that?
The idea is the following. Every process.
Figure out.
Yeah. Okay.
Read out.
Okay. So the idea is the following. So every process has a register which can be written by the process and read by all processes. Okay. So every process queries its failure detector module, accumulates more and more information about failures, and periodically it also reads the registers of other processes. So these registers, they contain the current view of this DAG, of this process. So you read the DAGs of other processes and incorporate this information into your own DAG. So if I, for instance, in this case, P prime, it knows that PGK has an edge to the vertex P prime, D prime, K prime. And then in its next write, it will put this information to its register, which is going to be read by all processes. And they also incorporate this edge to their DAGs.
I think I was asking something even simpler. How does the guy know there's an edge going to be there? Because he wrote the register, that's the right.
Yeah.
So he wrote register 1.
Yeah.
And this P prime read register 1.
Yeah.
Sometime later.
Yeah.
But how did anybody know that the value in register 1 at that moment was the value that...
Because P prime has stored this value, this information somewhere. So I skipped the step, but P prime, after that, there is a write step. Okay? Which is a write of this information, that PGK was before P prime, D prime, K prime. And everybody who's doing some computation later will get this information. Okay? And everybody is sharing. So the idea is that you do it forever. So in every round of computation, you repeat the same thing. You query failed detector, you check the register for other processes, incorporate all the data together, write it again. Okay? So I stop here. We define this tagging. So since we use reliable communication, which means that whenever I write some information, it's going to be read by all correct processes eventually. And this means that all these simulation forests which are computed at different processes, or in our case at the correct process, we don't care about faulty ones. It's going to be, it tends to the same infinite simulation forest, epsilon infinity. Which implies that eventually the tags of each vertex in our trees will stabilize. So since the tree is growing, it gets more and more, every vertex gets more and more descendants. So the set of trees cannot shrink, it can also only grow. But it will stabilize at some point. If it's already bivalent, it cannot get more. If it's univalent, it can become bivalent, but it can stay bivalent forever. But there is some moment of time after which every vertex has a stabilized set of tags. We call it valence. And the other thing is that every forest computed at the correct process will be eventually shared by all correct processes. So I computed some simulation forest, and eventually it's going to be a sub-forest of forests of correct processes. This is just because we have registers for communication. Because there's no any moment of time where they have the same forests, but the information is shared eventually. So the key idea of the reduction algorithm is that periodically we use this simulation forest and we extract the output of omega n from the current simulation forest. So we do it in every round of computation. So now we're going to consider a special case in the computation. And we assume that this simulation forest contains a certain subtree, which we call a rake. In this subtree, there is a pivot of the rake, which we denote by C, which is some global state of the simulated system. And there is a set of executions, which we denote by capital E. So this set of executions leads to a set of resulting states. And we assume that for any execution in the set, the resulting state is bivalent, univalent. And we also assume that there is at least one zero-valent state, and there is at least one van-valent state. Okay, so the state C is bivalent by definition, and the resulting states are all univalent. Moreover, we assume that in all these executions, every process takes exactly one step. And moreover, this step is on a shared object X, which is an object of type T, which is given to us, concerns power n. So in this scenario, we have R, which accesses X, then we have P, which accesses X, and then we have Q, which accesses X. Or in the other execution, we have the same, but in the other order. Since the order is different, then the resulting responses from the object can be different, and the resulting state of the object can be different. So that brings us to the one valent situation, one valent case in this case, and one valent zero valent state in this case. This is the configuration. Okay, so this is a rake. And we are going to use some kind of indistinguishability argument. So we claim that in the set of resulting states, there are two states of different valence. One is zero valent and the other is one valent. Such that at least k minus n processes, we denote the set of k minus n processes with the set of, with u, are confused. They have the same states in these two global states. Okay? Intuitively, that implies that there must be at least one correct process in the rest of the system to tell these guys the difference between the states. So how we locate these states? So we construct a graph. The vertices of the graph are the resulting states after applying all these executions of E. So by construction, they are all 0, 1 valent, and we color respectively the states. And we connect two vertices of the graph with an edge if at least k minus 1 processes cannot distinguish the corresponding states. If we want this graph to be connected. So suppose it's not connected. It turns out that we can present an algorithm which runs in the system of n plus 1 processes. And it uses objects of type T, actually just one object of type T, and a collection of registers. And this algorithm can solve consensus in the system, which is a contradiction. So the idea is that we use this graph, which is disconnected, for simulating a system of n plus 1 processes, simulating a system of k processes in the system of n plus 1, and we solve consensus, which brings us a contradiction, because we know that consensus power of T is n. Okay, so that's, I'm not going to go to the details, but this is a key idea. So since K is connected, and it has vertices of different colors, so there is at least one pair of neighbors of different colors. So now we locate this set of confused processes. You know that there is at least K minus n processes which are confused. And thus, these two states can differ only in the states of processes in pi minus u, in the rest of the processes. And one-shot object x. But x is one-shot. And every process has already invoked an operation on this object. So it cannot reveal any information afterwards. So let's assume that all processes in pi minus u are faulty. That implies that there is necessarily an execution in which faulty processes do not participate, because faulty processes, by definition, they stop taking steps after some moment of time. So there is an extension of these two states in which only processes in U take steps. And processes in U, they have identical states in both of the states, E of C and E prime of C. So they can never distinguish the execution which extends E of C from an execution which extends E prime of C. Okay? So they can never take a decision without violating the consistency of our construction. Okay? So that brings us a contradiction. Thus, there is at least one correct process in the rest of the system in pi minus u. So now we use this information to extract omega of n. And this is done as follows. So assume a stable in the sense that it doesn't change its valences anymore. A stable rake is located in the simulation forest. And given this stable rake, we can locally compute the set of at most n, that was supposed to be at least k minus n confused processes. Thus, the rest of the system, which is of size at most n, must contain at least one correct process. And we use this set as the output of omega n. So the result is that omega n is emulated. Okay?
Why there must be a stable.
Why?
why there must be a stable loop.
Not necessarily. This is a special case of the computation. All the other cases are simpler. This is the only case where we actually use the fact that we use atomic objects of consensus power n in the computation. The rest of the cases is simpler because they are all reduced to some scenarios in which the properties of registers are used. This is not very interesting in a sense because it already existed before. This is a new thing. In some cases, stable rake is never located. But it turns out that if it's not located, then the situations are simpler. Okay, so it's pretty technical, but I try to give the intuition of the most interesting case. Okay, so just to summarize, so I try to convey this message that the failure detector abstraction is convenient for describing minimal synchrony assumptions for various problems in distributed computing, in particular consensus problem. And in the thesis, we defined a number of weakest failure detectors for various synchronization problems, and for example, solving a non-blocking atomic commit, solving fault-tolerant mutex, and boosting the consensus power of atomic objects. And if you are interested in more details, I would refer you to the references, and the result I just presented. The original version of it appeared in DISC 2003, which is a symposium on distributed computing. And now a revised and generalized version of it is submitted to a journal. The weakest failure detectors for various fundamental problems of distributed computing were presented at POTSI last year. And that includes the weakest failure detector for implementing registers in the message passing, for implementing consensus regardless of the number of failures, and for solving non-blocking atomic commit. And the failure detectors for the use of failure detectors for mutual exclusion is explored in our submission to Journal of Parallel Distributed Computing, which was published in February. To give you the references about the other stuff I've been doing, so the lightweight probabilistic broadcast algorithm was presented in a paper in ACM Transactions on Computer Systems. The delta reliability, the probabilistic measure of broadcast reliability, was presented at ICDCS last year. And this year we published a paper about impossibility of boosting distributed service resilience. So now we restrict the fault tolerance to be resilient to a certain number of failures. So progress is guaranteed whenever your number of failures in your execution does not exceed some predefined limit. And we show that without any information about synchrony, you cannot boost the resilience level of your system. And some recent observation on the intersection of algebraic topology and distributed computing was presented in the workshop on using geometrical and topological methods in concurrency in distributed systems in GetCo. And the most recent result is on exploiting the absence of contention in the distributed system using only reads and writes. And this we just recently submitted to DISC. And I don't know how much time I have. Yeah, that's all right. Okay, so I have a few minutes. So if you're interested, we can discuss any of these topics. I'd be happy to discuss any of these topics, maybe offline. But since I have a few minutes more, I would try to say a few words about the last result. In a sense, all this story using this assumption that failures is the main obstacle for achieving synchronization in distributed systems. A different perspective can think that it's actually not because of failures. It's not because the process failed at the wrong time and so on. It's because processes conflict about shared resources. So we can say that the main obstacle is contention. So just processes, they come at the wrong moment and do something in the shared memory. And that prevents all of them from making progress. And it is often argued that contention is actually rare in practice. You can say, okay, in practical settings, it's usually the case that a process comes to the system to do something. And it is allowed to run alone sufficiently long to make progress. So then it stops and lets other processes do. Or we can, using some operation system mechanisms, we can use contention management to make things work this way. So it's, in a sense, it's a question of failure detection versus contention manager. Or we can, if we don't have any contention manager, we can be optimistic. And we can try to design algorithms which are which exploit the absence of contention. So we assume that the algorithm is always guarantees safety. So it never violates safety conditions of our implementation. It never lets anything bad to happen. But liveness is preserved only in the absence of contention. What is contention? There are different opinions. So we define step contention, which is in our case, we think that it's the most suitable notion for shared object implementations. So, and the interesting thing is that this kind of approach allows us to implement any object using just simple reads and writes. But it turns out that it brings also some inherent costs. So the time to execute an operation on a shared implementation is proportional to the number of processes which are concurrently active. They might not be doing anything at any moment of time, but they didn't finish their started operations. And you have to care about this prefix of execution. So the number of steps you take is somehow, it depends on the number of operations which are started so far. So there are a number of possibility and impossibility results which are very interesting, and I found this topic very interesting. And particularly, this similar approach is also used in software transactional memory, where instead of concurrent threads of computation, you have concurrent transactions. And sometimes transactions, when they conflict, they can abort. But the property we guarantee is that a transaction which runs alone without conflicts, it should commit. So it's a similar optimistic view of the execution. And I don't think this kind of result is limited only to distributed systems. But I found this topic very, very interesting. So that concludes my talk, and thank you very much for your attention.
Failure detectors are kind of mathematical abstraction of techniques like timeouts that equalize messages and so on. And some of the failure detectors that show up in literature is obvious how you implement them. Other ones is not so obvious how you would. Where would you put these weakest failure detectors on a scale of obviously implementable to not so obvious?
Well, to be honest, I don't know how to measure implementability of a failure detector. If you think about this concrete failure detector, omega n, I think it's closer to implementable ones, because there is a bunch of research on implementing omega in different timing assumptions. Like, for instance, there is a process and execution outgoing link of which are eventually timely. So this model seems to be appropriate for implementing omega. So I think you can devise some kind of assumption like this for omega n too. So in this sense, but it's a separate trend of research on failure detectors, how we actually implement them in the software. It's also very interesting. But this part of the research is devoted to the mathematical problem of defining the weakest failure detector. Yeah. I didn't get the question, sorry. This failure detector was defined before, right? But in the other results, we define new ones. Yeah. all other results are introducing new ones. So which means that we also had to give an algorithm, a machine algorithm, because a failure detector is a tight lower bound in a sense. It's weakest failure detector. So we present an algorithm and we present the lower bound. Yeah. Yeah.
So it seems like but in a shared memory, relation between contention and failure detection? Non-distributed setting.
Well, for instance, in this transaction business, traditionally you don't assume failures. I don't know, at least to my knowledge, people concentrate on the cases where everybody is able to take unbounded number of steps in any computation. So I would say that it's more appealing to device contention managers for such settings than failure detectors. Did it answer your question? I didn't say that it's like similar approaches. It's different perspectives, I would say. So it's not like there's one to one. No, I didn't mean this.
So earlier on you said if you have compare and swap, you can get infinite consensus. So the obvious question is, why not use compare and swap?
Well,
it seems like a very modest kind
right.
I used to think of compare and swap in the hardware provider.
Yeah. The usual answer is that compare and swap is considered to be expensive.
And this is going to be cheaper. All this
I don't know. I don't know. Before saying that something cheap or not, we should define this thing. So that's what we do. Of course, if you always given cheap compare and swap, which is fast and available, then.
But for practical purposes today, would you recommend using one of these more sophisticated things?
I think. Yeah, this is a tricky question. On one hand, this is for distributed systems. All these results, and the distributed system in the usual definition is compared to internet. So we have many processes, delays are unbounded, and so on. But in this talk, I consider shared memory, which seems to be a very expensive communication primitive, especially for internet. So this. I agree. There is some kind of tricky thing. I don't know. So, okay, I would probably stick to this answer that compare and swap is expensive, and we want to avoid using it. So let's stick to that. But I think if you just be practical, then you might think, okay, why using this failure detectors? What is it? And why using timeouts in the concurrent programming? Seems stupid, but I think it's somewhere on the edge between this concurrent approach and distributed approach. So this result is using something from both worlds. But okay.